In the first three videos, we talked about the definition of continuity at a point and continuity on an open interval. We defined the one-sided limits, and therefore we defined the continuity on a closed interval. We also used the properties of continuity, and now we're going to have a cool application of continuity of a function, and this application is called the intermediate value theorem. In the next slide, I'm going to bring up the definition of that just to see first, but I'm going to go through examples to make this concept solid in your mind. So let's check this theorem. So let's say like we have a continuous function on the closed interval, and we know how to check continuity on a closed interval. Okay, because that's one of the learning objectives that we achieved so far. And we want f of a is not equal to f of b. So in other words, at the end points, I want the function to attain different values. And let's say like k is a number between, k is a value, in other words, between two function values at a and b. So the conclusion says that there is at least one number in the interval a and b, and that number is c, so that f attains the intermediate value k at some point c. So this c is guaranteed by the theorem as long as the conditions of the theorem are satisfied. And what are the conditions again? Number one, let me just list here. Number one condition is that we want f to be continuous on the closed interval. And number two, we want f of a not to be equal to f of b. So as long as these two conditions are satisfied, there's always an intermediate value that's achieved at least one number c in the interval a and b. And here's a cool graph to explain this concept. Let's say like we have the interval a and b here, closed interval a and b. As you can see that the graph looks to be continuous because you graph this function without taking your hands off from here to here. And we have the first condition satisfied, continuity on a closed interval. And the second condition is that f should attain different values at the endpoints. Here we go. I have different values achieved at the endpoints. So this theorem says that this theorem guarantees that if there is an intermediate value k, that must be achieved at least once in the interval a and b. And in this particular case, k is achieved three times. One is here, another one is here, and another one is here. And there are three different points, C1, C2, and C3, in the interval closed interval a and b, so that f of c is equal to the intermediate value. Well, as I mentioned earlier, continuity is a big ingredient for the intermediate value theorem. And if the function is not continuous, there's no guarantee of that intermediate value to be achieved. And here's a cool example of that. If you have a jump discontinuity at an interior point, obviously from this value to this value there's a jump. So if k is chosen to be an intermediate value from the lower end to the upper end in a jump, well, this value is not going to be achieved at all in this particular case. So in other words, there's no point in the open interval for which f attains the value of k. And what failed here? Well, continuity of the function on the closed interval is failing here. For that reason, intermediate value theorem is not applicable. Intermediate value theorem has a very cool application in numerical analysis, especially when you have a function which is continuous on a closed interval. And if you want to find the zeros or locate the zeros of that, intermediate value theorem is very, very helpful. So here we're going to, in fact, use the intermediate value theorem to come up with the zero of a cubic function. Here we go. We have a cubic, and that is continuous on the closed interval 0, 1. In fact, polynomials are continuous on the entire real line. So this question is asking to use the intermediate value theorem to show that the polynomial function has a 0 somewhere in this interval. Okay, in other words, f becomes 0 at a point c, let's say C here, and C is in 0, 1, and that could be just one C. Maybe there could be two C's or three C's for which f of C is 0. We'll check, okay? But we need only one because it says like has a 0, so spotting one by using the intermediate value theorem is enough, okay? So as I said, f is continuous on the closed interval. We're awesome. We look at the endpoints. They must be different for me to apply the intermediate value theorem. So f of 0 takes you to -1, and f of 1 takes you to 2, and -1 is not equal to 2. Okay, that's good because f attains the value of -1 on the left endpoint, and as well 2 on the right endpoint, and 0 is an intermediate value, right? So for that reason, 0 must be achieved because you have a continuous function, and it must be corresponding to an interior point C in the closed interval 0 and 1. And in other words, 0 is achieved, as I said, right? So f of A is less than 0 is less than f of B, right? 0 is in between the function value is attained at the endpoint. So 0 is an intermediate value. And if you graph this function, you can spot at least one, well, in this case, it's 1, 0 for this function. And you can spot that there is 1, 0 because the graph of the function intersects x-axis. And the intermediate value theorem only tells you the existence of zeros, but the theorem doesn't tell you exactly what those C's are. So that's another algebraic question. In fact, in this particular case, you're going to set x cubed plus 2x minus 1 to 0 and try to solve this cubic equation. There's a cubic formula which is hard to memorize, but you can use the cubic formula to come up with this C point in between 0 and 1. And in fact, if you want to have a numerical approach, this is mostly for honor students, and check this bisection method. This is a very well accepted numerical method that we use to approximate the zeros of continuous functions. And please check this out if you're interested. All right, by covering the intermediate value theorem, we're done with all learning objectives of this section. All right, please go ahead and then start the recitation video. So you have a lot of exercises to cover. And then if you click the watch the video part here, you can actually get to my YouTube video, and then you can watch the solution with step-by-step approach. You have another example here for a piecewise function. You talk about the continuity of this piecewise function. You have another problem where you explore the points where you have non-removable discontinuities, and one more and probably another. Please check for your own reference, and this is the end of this video. Thanks for watching. I'll see you in another video. Bye.